Here's a podcast on atomic structure for chemistry. So I skipped the first few slides because they're just more about the history and the development of the atom. And the first concrete person we get to is John Dalton. And in general, what John Dalton said was that the atom is a solid sphere. He came up with these different tenets of atomic theory. And the one that stands out is this one here. He says atoms of the same element are all identical. They are not. So this is not true because there are these things called isotopes, and here's a representation of an isotope. Is the same type of atom, but it has a different mass because there's different numbers of neutrons. So again, what he really said is the atom is a solid sphere. He didn't know anything else about it. He didn't have technology to prove otherwise. Some other people we're going to look at with atomic theory. So we looked at Dalton. I'm just going to look at this little mnemonic or acronym, T for Thomson, R for Rutherford, and B for Bohr. And that's how I remember it because it goes in that order. And to myself and the little people in my head, I say this is D or B. So Thomson, his contribution is that he discovered the electron using a cathode ray tube. Sometimes his model is referred to as the plum pudding model or fruit jello. Who wants jello with fruit in it? It just sounds awful. Anyways, he used this thing called a cathode ray tube. And the gist of his experiment is that he's like, there's something negative going on in an atom, and I'm going to call it an electron, and I just think it's embedded throughout the atom. But that's all I know. And next we move on to Rutherford. He did this experiment called the gold foil experiment. His model is sometimes referred to as the peach pit model because peaches have these stone pits that are dense and hard in the middle, and essentially that's what he did. He said, the atom must have a nucleus that comprises most of the mass of the atom. It must be pretty dense, and it's positive in charge. So here's this gold foil experiment. He took uranium, and uranium's radioactive, and out came these positive alpha particles. He shot them through a really thin layer of gold foil, and he put this fluorescent screen around it to see what they were doing. And hopefully he put a lead block around that so he didn't get radiated, but who knows. And what he expected was for it to go straight through the gold foil, and some of them did. But then some of the particles actually got deflected, and some went back at him, or back at the source. And what the conclusion was is that in the atom there must be something really dense, so dense, in fact, that when you fire something positive at it, it bounces off of it. So it must be the same type of charge in there, and it's so dense that it bounces off of it. But sometimes the alpha particles go straight through the atom, hitting the empty space. And then Bohr's model is kind of the quantum mechanical model. He said that atoms have electrons that travel in kind of planetary orbits. So his is called the planetary model. And today's model is called the electron cloud model. So we're not really going to talk about the size of an atom. The size of an atom is small. And then you could read about these quarks if you'd like to. They're a little quirky. So what I might ask you on a test is, like, do you know what the symbol for an electron, proton, or neutron is? So E, E minus, P plus, N with a naught. And where are these subatomic particles located? The electron's outside the nucleus, the proton's inside the nucleus, the neutron is also inside the nucleus. And an electron really does have a mass, but it's so small that they came up with this idea of, let's just call that one 0, and each of these we'll call 1. So the mass of an atom is in the nucleus. You can look at the masses here. They're each 1, and electrons are outside the nucleus, and they don't have a mass, so to speak. And electrons are -1, protons +1, and neutrons are neutral, or no charge. So using this periodic table, this looks a little bit like one side of your periodic table. These things here, 2, 8, and 1, those are the electrons in the energy levels. And the 2 is the one closest to the nucleus, and then the 8 and the 1. 11 is the atomic number. That's the element symbol. That's the element name. And this is the average atomic mass. Sometimes I ask you to give me the mass number. So you'd look at the periodic table. You'd look at that number and you'd round it. You'd either keep it the same or you'd round it. In this case, you'd round it, because that 9's there, you'd round it to 23. The mass number is always a whole number. So formulas you need to know. The atomic number is always equal to the number of protons. AT stands for always true. So the number of protons determines the type of atom it is. It's also the same as the number of electrons in a neutral atom. So protons equal the number of electrons if the atom is neutral. The mass number, which is a whole number, is equal to the number of protons plus the number of neutrons. And these are in the nucleus. And again, the mass number is it's always true that it's a whole number. If you rearrange this equation and put neutrons here, you'd get neutrons equal mass number minus protons. So again, electrons equal the number of protons in a neutral atom. Something that's not neutral will have a superscript up here with either a plus or a minus. So this one's a 2 plus, that one's a 1 plus. We don't put the 1 in front of that. Like that's a 2 minus, and again, we don't put the 1 in front of that. So here is a little chart to fill out. So hydrogen, what's the symbol for hydrogen? It's H. You look on the periodic table, it's atomic number 1. The atomic number and the protons are always equal, so there's 1. And to find the neutrons, it's the mass number, so maybe we better fill out the mass number. You look at the periodic table, and hydrogen's mass number is 1. So to find the number of neutrons, it's 1 minus 1, which is 0. And the number of electrons, for this whole chart here, the protons will be equal to the electrons, since they are all neutral. And then we have helium, and we could write out helium. It's atomic number 2. If it's atomic number 2, it must have 2 protons. So I'm just going to skip around here. So if you have an element that's atomic number 3, it's going to have 3 protons. And if you have an atom with 8 protons, it must be atomic number 8. So I'll go back up here. We can't find the neutrons yet. The electrons are 2 because the electrons and the protons are equal so far. We don't know anything else about electrons. And the mass number, if you look on the periodic table, the mass number for helium is 4. So you just keep it at 4, round it to 4. And to find the neutrons, you'll go 4 minus 2, which is 2. Atomic number 3, I believe, is lithium. And the protons will be 3. And I should go over here. The electrons for that one are going to be 8. And the mass number of lithium, I got to take a check on my periodic table. That's not in front of me yet. And lithium says it is 6.9. Mass number has to be a whole number, so we'll round it to 7. And to find the neutrons, we'll do 7 minus 3, which is 4. Now we go to this next one, which is atomic number 8, which is the element oxygen. And the mass number on that rounds to 16, and 16 minus that 8 over there is 8. Now this last one's weird. It says a mass number of 39. So look on there and find something that has a mass number of 39. It looks like it's potassium. And potassium has a mass, an atomic number of 19. The number of protons must be 19, and the number of electrons must be 19. So to find neutrons, we'll go 39 minus 19, which is 20. Isotopes. So Dalton was wrong. Atoms of the same element are not identical. Atoms can have isotopes where they're the same number of protons, but they have different numbers of neutrons. So this leads to different mass numbers. So atoms with different numbers of neutrons than normal, I call the periodic table normal, even though this isn't technically true, are called isotopes. Let's see. So when you do your WebAssign, you're going to see a notation like this, and this is the chem pad. That gives you the bottom number, and that one will give you the top number. It doesn't matter which one you do first. If you hit that bottom one first, it actually gives you an underscore, and then you type in your number, which in this case would be 10. And then you hit this button. Sometimes you have to hit it twice to get a caret. And then you would type in the number 20. And then you would type in neon with no spaces. So what I'm really getting at here is this new symbol. So here is where you write the element symbol. This bottom number that goes down here is always the atomic number, which you could say is also always the number of protons. And the number up here is always the mass number. So if you look at this one, the mass number is a whole number. So neon has a mass number of 20, and it has an atomic number of 10. And you can look at the periodic table and see that neon says on here it has a mass of 20. So this is not an isotope. That's like a regular neon. Who doesn't love regular neon? Isn't it the best? So some symbol practice. So number of protons is 9. Which you could say is the atomic number, so you write it there. The number of neutrons, that's not going to help us out yet. Number of electrons is 9. We don't need to, if our electrons and protons are equal, we don't need to do anything about it. Atomic number is 9. So again, 9 is written there. Mass number is 19. So the 19 goes up there. Or you could add the neutrons plus the protons to get you 19. and then of course the letter F for fluorine. So here is another element. Number of protons is 35, so that's atomic number, so I would put that right. I would put it at the bottom left is what I should say. Number of neutrons is 45, so I might go 35 plus 45, and that would give me 80, which is the mass number. The electrons isn't telling us much here. Again, the atomic number came from there or there, and the mass number was here, which we already figured out. I think we had enough symbol practice. Sometimes you name isotopes a little bit differently. For example, here is carbon. So there's a couple isotopes of carbon. There's a carbon that's 12, so you could write carbon-12, or you could just put the 12 in the carbon. And there's a carbon-14, so you could do carbon-14, or you could do 14 in the carbon. And the same with this uranium-235. You could do 235 and uranium. So let's do some practice here. So I got hydrogen 1, 2, and 3. So the symbol, if we do it the proper way, hydrogen, these are all atomic number 1. And again, I'm writing this with a mouse. So these are all atomic number 1. But this one says it's hydrogen 3, so there is a mass number 3. This one's hydrogen 2. It has a mass number of 2. Wow, that's a doozy. And this one has a mass number of 1. So the protons are all 1. And these are all neutral, so the electrons are all 1. Now the neutrons will go 1 minus 1 is 0. So the regular hydrogen has 0 neutrons. This one is 2 minus 1, which is 1. And this one's 3 minus 2, which is 2. So the mass number is 3, the mass number is 2, and the mass number is 1. Now these other ones are a little bit different. We have carbon-12, so a carbon and a carbon. We have carbon-12, and carbon, if you look on the periodic table, is atomic number 6. And we have carbon-14, which if you look on the periodic table is still atomic number 6. Number of protons, still 6, and 6 are electrons. These are neutral, are 6 and 6. And to find the neutrons, we'll go 12 minus 6 is 6. And in this one, we go 14 minus 6, which is 8. And the mass number, it told you was 12, and it also told you it was 14. So we'll work on these other notes another day.